Hey everybody, welcome to Chapter 5, the normal distribution. This is, we'll cover section 5.1 here, and this is part 1 of 2 recorded lectures for section 5.1. Alright, so we're going to get into talking about the normal distribution. I think we're all familiar at this point with what it looks like, okay? It's a bell-shaped curve with symmetry about the mean, right in the middle, mu. This curve is a normal curve, right? And it deals, it describes, this is a visual representation of the behavior of a normally distributed variable. All right, so if we have x behaves in such a way where the majority of the observations, 2/3 of them, by the empirical rule, clump in here around 1 standard deviation of the mean. 95% fall within 2 standard deviations of the mean, and then unusual observations we say are out here, more than 2 standard deviations away from the mean, either 2 standard deviations above the mean, like an unusually tall person, Dwight Howard, or the guy from Game of Thrones. In terms of height, he would be somewhere over here. Alright, so I want to talk about the NFL Draft Combine. For those of you that aren't familiar with it, every year, NFL players go through a battery of tests, and it's called the NFL Combine. And basically, these great college players are all evaluated, and lots of data are collected about them in a lot of different categories. Like, they want to see how strong you are, so you do the bench press. You bench press 225 pounds as many times as you can, and they track that. You do the long jump, you do a lot of running, the 40-yard dash, which we'll be talking about in just a moment. You also take an IQ test, which is called the Wonderlic, is what it's called, the name for it, this specific IQ test. And there's a lot of psychological testing as well. But basically, before an NFL team decides to commit a bunch of money to a player, right, before they commit a bunch of money, they put them through lots of tests, all right, see how they respond, all right? So they want to make the best decision possible. And let's talk about a specific position in football called the wide receiver position, WR for wide receiver. All right, they are individuals that catch a football, they run routes, and the quarterback, there's the football, throws them the ball, and they catch it. And that's their job. All right? So they want to make, let's say they want to draft the best wide receiver they can. Well, how do they determine what the best wide receiver is? Well, they're going to look at his game tape. They're going to talk to his friends and colleagues, his old coaches, all right? Maybe look at his transcripts. But at the Combine, they're going to put him through a bunch of different tests, all right? Probably year after year, the most important test for wide receivers is the 40-yard dash. They want to know how fast can you cover 40 yards in a controlled environment. All right, so everybody has the same chance. They all put on their cleats, and they all line up, and they go 40 yards, and they time it, all right? So the question is, how fast can a particular player run the 40-yard dash? And that has such a big bearing on where these guys get drafted. It's really amazing. A hundredth of a second makes all the difference in the world between millions of dollars getting picked in the first round and being on TV, and getting picked at the end of the draft, the 7th round, and having to just scrape by in life on a couple $100,000 per year. All right, at the NFL Draft Combine, and by the way, I joke about scraping by, but the reality is that the careers of NFL players are very short. They're very short. I think under 3 or 4 years on average, and these are for players that get drafted. If we say x, the random variable x, equals the 40-yard dash time, so it's just a sprint, 40 yards, for a wide receiver at this Combine, it is normally distributed. I have the data, and it's normally distributed. The mean is 4.86 seconds, and the standard deviation is 0.23 seconds. Alright? The mean is the center of a normal curve right here, and the variability, that goes left to right. That's the standard deviation, how much spread there is. Alright, so we have a mean of 4.86 seconds and a standard deviation of 0.23 seconds. These are the two things that tell the distribution how to behave. With the binomial, we had two things. We had n and p. We had the number of trials, and we had the proportion of probability of success. With the Poisson, we had mu, just the mean. Here we're back to having two things. Alright, and we have 4.86 seconds in this case is the mean, and the standard deviation is 0.236 seconds. 0.23 seconds. Alright? So, clearly running faster is better. If you're a guy trying to strike it big, you want to be over here. Alright? If you're over here, you're not going to get drafted. You're not going to be recruited as highly as somebody on the other side of the curve, alright? And if you're over here, your name is Danny. Alright? That's Danny. Now, we can do a lot of cool things with the normal curve. Once we know that we have a mean and we have a standard deviation, we know the data are normally distributed, we can ask questions like, how special is it to run a 40-yard dash in 4.4 time? A 4.440 is a very common expression in sports. For those sports fans out there, have probably heard it, all right? Well, what z-score is this? What percentile is this? How special is it? How unlikely is it? We can answer all of these questions this chapter. Let's talk about the properties of the normal curve. Let's break this thing down a little bit, all right? So the graph of a normal distribution is called a normal curve, which this isn't our first rodeo, as they say. All right, we've certainly seen the normal curve here several times before. All right, we'll be drawing lots of them this chapter, so you might as well get used to it. All right, work on drawing your normal curves. All right, I want you to take a moment, practice your normal curve. It should look something like this on the left. All right, I don't expect you to make a normal curve as beautiful as mine. All right, but it should look like that. It shouldn't look like this, like some kind of mushroom formation. All right, that is not good. All right, because the reason why is because we want to make it clear here a few things. The first is that the mean, the median, and the mode are all about equal. All right, and the curve itself is symmetric about the mean mu. All right, the total area under the curve from negative infinity to positive infinity is 1. An area with continuous random variables which we've discussed, all right? Continuous random variable is something we measure, all right? Continuous random variable area equals probability. When we were dealing with discrete data, we had these jumps from 0 to 1 to 2 to 3. We didn't have a specific interval like we have here. Here we have an interval from negative infinity out to positive infinity. The normal curve approaches, but it never actually touches the x-axis. It approaches the x-axis, it never touches it, and that's called an asymptote. I think we're all familiar with that from our good old algebra days, all right? So we say this thing is symmetric about its mean mu. All right? 50% of the curve is to the right of the mean, and 50% is to the left, and we've discussed the empirical rule. All right, why don't we go ahead and just throw it back to the empirical rule here one more time, draw another curve. All right, if we have a mean mu and we move over one standard deviation to the right, we move over one standard deviation to the left, we have approximately 68% of our observations. If we move over 2 standard deviations, and 3 standard deviations. In here we have about 13.5 because of the symmetry, and over here 2.35, and so on and so forth. Okay, so just like the empirical rule from before. All right, now when we're drawing pictures of these things, which is going to be a big strategy for us in this section, we're not going to draw the y-axis, but really the y-axis is an f of x. This is a smooth curve on the coordinate plane. Say you wanted to get a curve that looks like this in your graphing calculator, you could actually do that. A graphing calculator is not necessary for this course at all, but it's useful to think about things this way. If you plug this into your calculator, the following function, you would get a normal curve. Do a little bit of zoom in here. Here's the function. You won't have to know this function, but it's useful to think about in your off time. Maybe an idea for a new tattoo here. This is a giant exponent here, e, the base of the natural logarithm, and we raise it to this power here. 2 things control whether a normal distribution looks like this, really skinny normal curve, or if it looks like sort of a chubby normal curve. And then where are these curves located on the coordinate plane? 2 things control these. One is the mean. That determines where our curve actually falls on the x-axis. And then how chubby it is, well, that's based on variability, sigma. Chubbiness is sigma, skinniness is sigma. Where it's actually located, that's the mean. That's the center. Alright, so we usually don't draw the y-axis. The y-axis represents the height of this thing, and under the curve is probability. And all the area under the curve, between the x-axis and the curve, that's probability, and that equals 1, because it's a valid probability distribution. Same rules of probability distributions for discrete random variables apply for continuous as well. Continuous random variables can assume any value in an interval, and we represent this with a smooth curve. Any 40-yard dash time you can think of is a possibility. From 0, in this case from 0 all the way out to infinity. Alright, a normal curve can have any mean and it can have any standard deviation. Any mean and any standard deviation, as long as the standard deviation is positive. Alright? These 2 things, the mean and the standard deviation alone, determine the shape. We say the shape and the location. Of the curve. Alright, let's look at a couple different curves here. Suppose we had a data set where our mean was 50. I'm going to draw 2 curves, and let's see how these things are going to look different, even though they have the same mean. So we'll say they have a mean of 50 right in the middle. Alright, and then this one on the left is super skinny, very low variability. Maybe the standard deviation here is 5. And then over here, much thicker normal curve. Maybe it has standard deviation of 13. The larger the variability there is, the more spaced out we are from the center. It's harder to predict exactly what's going to happen. Isn't more area, more probability closely packed in here at the mean? Sure it is. Right here it's a lot more spread out. The graph on the right has much more variability, and that's represented by the sigma being so much smaller than the 13 over here. Alright? On the other hand, we could have a situation where we had the same variability in different and different means. All right, so let me draw one giant x-axis to describe this situation. All right, here's our x-axis. Suppose we have one curve that looks like this and one curve that looks like this. All right, and let's assume that we have different different means here, same standard deviation. So maybe our variability is 37 for each of these. But the means are, maybe this is 110 and this is 403. Same variability, different mean. So when we're dealing with the normal distribution, we'll see that we're going to be given a data set. They're going to give us a mean, and they're going to give us a standard deviation every single time. They're going to give us a mean, and they're going to give us a standard deviation every single time. A mean and a standard deviation. And it'll be our job to answer probabilities relating to this. Suppose we had a data set with a mean of 100 and a standard deviation of 15. This is IQ. Traditional IQ test has a mean of 100, standard deviation of 15. 50% of people have a IQ above 100, 50% below 100. So how are we going to answer the following? What's the probability of randomly running into somebody on the street and they have an IQ that's at some level of genius, 130? Maybe they're in Mensa. Well, we're going to have to use our table. The trouble is our table does not have a mean of 100 and a standard deviation of 15. It doesn't. It has a mean of 0 and a standard deviation of 1. That's okay. What we're going to do is pretend. We're going to enter pretend time, play time, fun time. We're going to pretend like our particular value in question, in this case or situation we're talking about, IQ. We're going to pretend like it has a mean of 0 and a standard deviation of 1, because what we're going to do is use the z-score and transform our data. If somebody's IQ is 130, their z-score is 2. They're 2 standard deviations above the mean. So in part 2 of this section here, we're going to look at exactly a bunch of situations here where we're going to be able to figure out the area under the curve given a z-score.